Thank you for inviting me. I will be concerned with dynamics. So no stationary Schrödinger equation. I will assume that somebody else has computed the electronic eigenvalues for me beforehand. So the problem that was just classified as being out of reach, I assume to be solved, and then I start working. So I look at the time-dependent Schrödinger equation with the naive wish that I would like to simulate a chemical reaction. So I really would like to see a molecule moving. And in terms of the timescales where quantum effects are important, so I'm thinking of femtosecond spectroscopy. So I'm thinking about photochemistry, and I want to do the simulations of that. So kind of to be really curious on what is the molecule doing, and I want to have a movie to watch. So I also have an epsilon in the game, like Sergio this morning, but I belong to the other camp. I don't have epsilon square, so it would, what Sergio said, you always have to put a square root for him, or if you want to convert from me to him, you have to square my results. I'm sorry, it's very bad that we have those two camps and you have to translate all the time. So the wave function that solves this equation is time dependent and space dependent, takes complex values, and what I have in mind is a semiclassical scaled Schrödinger operator. For me, I'm a mathematician, MS1, but as you like. And my regime is smooth potentials under reasonable growth assumptions, and this is kind of, so here all the dirt is under the rug, because I assume that somebody has solved for interesting nuclear configuration the electronic many-body eigenvalue problem. So I'm working beyond the Born-Oppenheimer approximation, and I wonder what happens if somebody else has sorted out for me what do the electrons do, what do the nuclei do once the electrons tell what they think. Okay, so the problem here is still interesting enough for at least two reasons. So it's dynamics in a high-dimensional space, yeah, and it's oscillatory motion due to the presence of this mass ratio here and the time scales you want to move on. So the idea is now again to make a decision between two camps. It's a high-dimensional problem, so or there are several camps, but I don't go for sparse grids. I don't go for tensor analysis or anything. I go for mesh-free methods. And the mesh-free methods I want to analyze shall be guided by underlying classical mechanics. So it would be the corresponding classical Hamiltonian system corresponding to the Schrödinger equation. So the surrogate for the high-dimensional wave function is a classical trajectory that evolves an initial phase-space point. Somewhere the replacement for the Schrödinger operator is this classical Hamiltonian energy, and V is the potential. So these are the two things. So the slide before describes the aim. The slide here is the tool. And the idea is to work with that tool and extract as much information as you can get from the classical point of view. So, as I have already said, this approach is motivated by the dimension of the problem. So you should think of having at least 10 degrees of freedom in the game you want to look at. So small molecules, something like ammonia, would be 12 degrees of freedom without symmetry considerations. If you want to go higher, 10, 20, 30 degrees of freedom. So that's kind of the target dimensions. And we have this semi-classical parameter in the game. It's safe to think that in the interesting systems, the mass ratio you have is somewhere around 10 to the minus 2, yeah, roughly speaking. So it's a small parameter, not awfully small, but small enough to be important. So the dream is to work for a contribution to the simulation of photochemistry. So I mean the best thing possible would be to contribute to simulation of the first step of vision, kind of the transformation from light energy into a vibrational energy. So so kind of the current all current models have a quantum core to it, which goes as follows. So there's this molecule retinal and rhodopsin. The idea is the corresponding wave functions is in some kind of rest, in some kind of almost ground state situation. Light falls on the molecule, you are excited, you start moving, and you start moving very rapidly into another configuration where the molecule starts shaking and creating the kind of the stimulus around the optic nerve. And the idea is somehow here to understand this kind of cycle process. And this is, of course, I mean, this is a extremely ambitious thing, yeah, right? I mean, you have tons of problems here in this picture. First question, represent your initial condition properly. Simulate excitation by light. What we will do today in this talk is simulate the passage on one of those potential energy surfaces. Next thing, transmission to another surface. And finally, this is a highly idealized cartoon, and I think the most severe problem is how to model interaction with environment, solution, etc. Yeah. So it's a thing, I guess it's a problem for several lives, but why not? Okay, and today the idea is to dwell a little bit about that passage here above, given a nicely prepared wave packet, and wonder how the guy is traveling on a high-dimensional surface. And what we have to keep in mind is that, so the yellow ghost sitting here is actually kind of a hairy, rather fluffy, hairy guy. Yeah? So what we have to do here is we are in a high-dimensional space. We want to chase a rather localized object. So I like to think about I want to sit on a flying carpet. So the carpet is flying, I have to sit on the carpet is fluffy and oscillating, and the key point, interestingly enough, the problem is not to sit on the carpet and to follow, the problem is also not somehow to qualitatively describe the fluffiness. The problem is to describe the size of the carpet. This seems to be the most difficult aspect of the game. So I will show you strategies which are really fine in terms of location of the carpet and what is kind of the fluffiness of the guy. The difficult thing is, strangely enough, what is the reasonable size of the carpet you need. Okay, so this is my agenda for the next half an hour roughly. Okay? Good. So this carpet analysis, I will do it in 4 steps. I will first talk about isolated carpet pieces, move them around and explain the basic ideas. I will get a bit kind of, this is traditional and very classic. I will do it in a variational way in a second level of thought. I will say a little bit about the error analysis, and then I will somehow turn a single carpet into a quilt, and I will patch together different carpets and see if I improve my approximation. Good. So let's look at a single Gaussian. So I have basically up to the epsilon business the same notation as Sergio. I describe a complex-valued Gaussian with a complex symmetric positive with a complex symmetric width matrix whose imaginary part is positive semi-definite in this factorization with a PQ inverse, where you need some constraints on the 2 factors that assure that you actually have a positive definite imaginary part, such that you actually have a square integrable Gaussian function, and you account for normalization, the way things are cooked up by a Q factor in front. So this is an extremely a nice way of parametrizing a multivariate Gaussian function that dates back to the 80s. This way of breaking up a complex symmetric matrix with positive definite imaginary part. So one way is kind of in the original work. Later, Christian Lubich looked at it again, and he found a kind of more natural condition to those that you see that the real and the imaginary part of those 2 matrices stuck together, they form a symplectic matrix. So you have the passage from the Siegel half space to the symplectic group. Or an alternative way, which is a bit more handy in terms of computation, is you stack those 2 matrices on top of each other, you have a rectangular matrix, and symplecticity translates into being a normalized Lagrangian frame, and then you work in the context of symplectic linear algebra with a tendency towards Kähler geometry. But it's just notation and words. So what these matrices here actually describe the size of the carpet. Yeah? So we have, when we take the modulus squared, we have a normal distribution where the covariance is described exactly by QQ star. And when you go for the Fourier transform and take the modulus squared, again you have a normal distribution, and then it is the P factor. And this makes this parametrization so handy because you can exchange between position and momentum, and you just jump from Q and P forth and backward, and you know where you are without too much calculations. Okay, so this is the way how to parameterize those carpets. The little Q's and the little P's tell you the center of the carpet where you are. the epsilon is somehow here working together and takes you how fluffy the carpet is, and the matrices there, the capital Q and P, tell you the size of the carpet. And now the idea is, if you start on such a carpet and you move on one of those potential energy surfaces, how do they change? And the answer is surprisingly easy if you just want to have a very rough answer. So you need a multiplicative phase, constant in front, a time-dependent constant. The centers move with the classical equations of motion. If you have written your width matrix in this QP factorization, you see the linearized equations of motion, and for the phase, it is the action integral. So that's it. For a Gaussian wave packet, solve the classical dynamics accompanied by the linearized equations, put the action on top, and that's it. And the error is square root in epsilon. So how do you prove? And the proof is, has already been alluded this morning to. So you linearize your Hamiltonian, that is a time-independent Schrödinger operator. You somehow morally insert the classical trajectories. You keep the Laplacian part, but you expand the potential quadratically around the center of the classical equation, and then you have a cubic remainder acting on a Gaussian. The Gaussian has a variance of order square root of epsilon. When you put something cubic on top of it, you get a 3/2. We are working on the long time scales, 1 over epsilon, so at the end of the day we lose 1 power due to time scaling, and then we have the square root of epsilon. So you see, it's depending on your wish for rigor, but it's a half-page calculation that tells you about accuracy here. So, and then you have in mind that as a rule of thumb, epsilon is something like 10 to the 2. You have here something which is a 1-digit approximation with some grain of thought. Okay, so this is not bad, but also nothing to be enthusiastic about. So, what can be done to improve? So one line of thought is the variational one. You still want to keep in the class of Gaussian wave packets. You still allow a prefactor, but you wonder somehow what would be the optimal center of the carpet and the optimal size of the carpet. And you do a variational ansatz on this manifold in the following sense. Maybe I show it here. So you let the thing evolve. So we are here at a point on the manifold. We evolve. We project down, on the tangent plane, and we take that thing here, the resulting equations of motion, where the time derivative is set equal to the orthogonally projected right-hand side of the original equation of motion, and P is the original projection down to the tangent space. So Dirac-Frankel variational principle with an ansatz manifold that is parametrized Gaussian wave packet. So what is the gain in doing it like that? So one of the gains is that by construction you get an energy preserving approximation. So here the proof of energy conservation is very quick. So we look at energy expectation, we differentiate with respect to time, we produce an orthogonal projector on the left and on the right, we sort the projector out And since we're working with self-adjoint operators, we see here a 0, and we are done. So this is an improvement over the previous thing, because in the previous thing we just somehow inserted the classical equations of motion and proved afterwards the accuracy. Here we go in from a more educated point of view with this orthogonal projections on the tangent space, and get a guarantee for energy conservation. Mass conservation is there as well. And when you then do the same analysis as before, you realize that you get equations of motion very reminiscent of the classical ones, but instead of the point evaluation of the gradient and the Hessian and the potential itself, you get averages of those guys along the Gaussian function you are actually building up. So what you're doing here with this Gaussian variation of wave packets, you're moving this Gaussian function, and to determine center width and prefactor, you have to average the corresponding entries of the potential along your solution. So in some sense, you're bringing in more information from the dynamics, in particular more information from the potential energy surface, since things are not centered at the core, but you take the average over the whole carpet and not just the point evaluation in the center. So this is an idea that goes back to Coulson and Carl Plus, to do it like that. And you revisit the old proof, and you see the same structure emerging as before. You split the Hamiltonian into two parts, the projected part and the rest. You realize that the projected part is a quadratic Hamiltonian, where here, instead of the Taylor approximation around the center, you have this average quantities. You have a cubic remainder, therefore a cubic remainder on a Gaussian means a 3/2 business, and again you lose one epsilon due to the time scale. So you have gained in terms of energy conservation, but in terms of accuracy you are working on the same level, and you have slightly more demanding equations of motion, because it's not point evaluations, but you have to do the averages on the support of the Gaussians. It's hard to say which one to prefer. I mean, for the other one you can use energy as an indicator that things are going wrong. Here energy is conserved. You can fight nicely about which one is better. Okay. So both things somehow qualify for one-digit approximations. Nevertheless, some people use it. Yeah. So, and what we did, I don't know why we did it. We looked at what is the accuracy of those two approximations when we look at expectation values. So the previous analysis was an analysis in terms of norm, to norm. So the calculation is not difficult. You revisit the same proof idea, but since you are working with expectation values, you get a remainder that involves a commutator with the remainder. And then you have here a cubic polynomial inside a commutator, which brings down the polynomial degree. Roughly speaking, a commutator means that you take a derivative. So we have a quadratic polynomial effectively standing here against a Gaussian, so we get a 2. And then we are here with one order higher. So the interesting observation is that the known error measure in L2 norm, which gives you this square root, comes with a better behavior once you look at the observables. Namely, you see a plane epsilon, which means in terms of the observables, both approximations give you roughly 2 digits. Yeah? Norm, you're bad. And here a 2-digit accuracy, I think, is in the game where the potential energy surfaces are anyhow bad, just the right thing. To expect more would not be appropriate. Good. So this is an analysis of a poor single wave packet. So you're moving such a single carpet around and you're trying to be very economic in putting it at the appropriate places with the right size. So, of course, I mean, you just need to think about a double well situation or whatever. It's clear that a single carpet is not good. And so now there's the idea Sergio alluded to this morning, that you build on top of the carpet an orthonormal basis and adding Hermite-type polynomials in front of it. However, even so, I mean, once the carpet is not good enough, you have to add a lot of Hermite polynomials on top in order to capture dynamics where actually, like in a double well situation, things are floating left and right. Yeah, it means that you have to go up in the polynomial degree a lot, and then somehow your perturbative term becomes a rather large term. So what I want to do now is I want to follow a different line of thought. So instead of sitting on a single optimized carpet and building on it, I want to kilt. I want to glue together different carpets and see what we can achieve by moving on different carpets. So this is the program now for the next thing, which is here. So the swarms. For the swarms, one uses one beautiful thing, which is a generalization of the Fourier inversion formula. So if you put in front of a plane wave, let's say, a properly centralized amplitude, you can view the thing here as a windowed Fourier transform, and you have a Fourier inversion formula if you do things properly and here things are written and normalized properly. You have an inversion formula for Gaussian wave packets. So, or another way of saying, you have an overcomplete basis set, or you have a Gabor frame, continuous Gabor frame, whatever you want to call it. You can use those those wave packets for a reconstruction formula. So what you can do now is you can view this inversion formula as a quadrature problem. We are in high dimensions, so we don't want to set up a quadrature grid. We want to do a Monte Carlo quadrature. So by hand, we introduce a weight. So we do an importance sampling, putting in the modulus squared of the coefficient, of the Gabor coefficient. We sample it, and we produce in this way a sum of Gaussians, of little carpets centered somewhere, and the different carpets are balanced to each other according to the Fourier coefficient. So this is a Monte Carlo, let's say, in function space, and you do the usual trivial estimate in Hilbert space, and you get the usual square root of n error estimate in mean square error. There's nothing surprising here. Let's have a look how it works. So it's a 1D example to see what is going on. In red, I have a moderately frequent oscillating wave packet. And now with the procedure outlined on the slide before, I place 10 different Gaussians balanced with the corresponding coefficients to produce a sum. And then the blue line tells you what the modulus squared of such a sum looks like. So this is an approximation with 10.
So the red dotted line is literally exactly a wave packet,
It's
a Gaussian wave packet.
It's a Gaussian wave packet, exactly.
Okay, and the other one is just translates,
Exactly.
weighted translates.
Weighted translates, so 10. So, I mean, you also see, I mean, I did a very rough Monte Carlo ansatz, even no symmetrization, nothing, just throwing in points. So this is what we get with 10. With 100, we are already very nice at the core, and it's just at the tails. And then 1000 is more than enough. Yeah. And the good thing, I mean, I'm not completely honest when I say it is dimension independent, because you all know in the variance there is always something dimension independent cooking up. But nevertheless, it's not immediately hindering you to go up in dimensions. Yeah. What I've shown you here in 1D works in 10D. Basically, it's the same. When I move and cut through wave packets and look, I see exactly this pattern here. And I don't need to build up a 10D grid in order to represent, I mean, this function is highly oscillating, right? So, and kind of the sin I commit is here in red, that I assume that I can sample the coefficients. So here, a priori knowledge or hard computation goes in when I actually have to compute. But once the coefficients are there, the procedure here tells you how to build a weighted superposition to represent the guy. And now we have worked carefully to be able to optimally transport an individual guy. So now we do them all together. So this is the first idea, which also has the name Gaussian beams in other contexts, although not for the Schrödinger equation, but for other evolutionary PDEs, porous medium, whatever people compute with Gaussian beams. They have a representation of a function in terms of Gaussian beams, and they let the individual beam evolve under classical equations of motion. So that is what I write here. I pull the unitary evolution on a single Gaussian, and I let the single Gaussian evolve, as we just discussed earlier. And the interesting thing is that the Gaussians together, the swarm, are better than the individual Gaussian by itself. You remember we had that square root epsilon approximation, all of them doing together simultaneously the same thing, but everybody has its own classical mechanics. Altogether they are better. They move from a square root to an epsilon. So the first proof of that is due to Zheng in 2014. It had been observed years before that there is something going on in the swarm that is kind of same information, but the swarm is better than the individual members. And there is a rather heavy paper using WKB analysis to explain this effect. An alternative approach is called a frozen Gaussian approximation, which goes back to the 80s. And it's due to two chemists, Hermann and Kluck. And what they devised was the following. So you have your initial Gaussian, and you just move the core. You leave the size of the carpet unaltered. Just move the carpet, but you readjust the internal distribution between the different Gaussians. So the individual building block is frozen, it's just moving, but the size is frozen. You don't allow the carpets to thaw, but you allow for a readjustment of weight a long time. And the magic formula for the readjustment of the weight is again a formula that is purely in terms of classical dynamics. Again, it's entries, vertical derivatives of the flow in a corresponding combination. So again, you extract it from the linearized equation.
Yeah, so the A depends on Z also. That
Exactly.
was
So
rather
every frozen Gaussian gets its own new readjustment factor depending on the original center. This is rather it's rather surprising, and when Hermann and Kluck came out with that thing in the 80s, there was a series of papers where it went forth and back. This can't be true for physical reasons. Then another paper, yes, it must be true for physical reasons, etc., etc. And from my point of view, it was actually my first PhD student, Torben, together with a postdoc, Rus. They proved that the readjustment is correct in the sense that it produces an epsilon approximation. It took a long while until, and then 1 year later, Didier Robert produced another proof. So what is that mysterious swarm communication that renders this group of Gaussians into something that is every individual one works as if he were alone, right? It's an embarrassingly parallel approximation. Every Gaussian is doing its own business. Also, in the frozen approximation with the readjustment, the adjustment of the factor comes from the Gaussian. There is no communication between the Gaussians, whatever. How the hell can it be that if I feed everybody with the individual information, that as a swarm they are better than everybody by himself? And the best explanation I can offer goes as follows. So either one, the thought or the frozen Gaussian approximation, you can write it as an horrendous oscillatory integral where you put all the stuff from the Gaussians into a big f function. And then, for reasons I cannot explain, you compute a vertical derivative of that f function. And then the miracle happens. When you do the calculation, you realize that the derivative doesn't depend on the initial function you are actually propagating. And then you're free. Because then you can start manipulating. You don't touch the initial function that is linking everything. You're just manipulating up here. You do partial integration. And since you have 1 over epsilon here, once you start turning the crank here, you earn additional epsilon powers. And by that partial integration, you also compute the appropriate reweighting factor. It has this wonderful simple form that it is the vertical derivatives of the flow. So what I have presented you is an analysis of the building blocks, where I actually cannot say what is better if you do the plain stupid semiclassical approximation or the more advanced variational one. Both of them have the same accuracy. The variational one is energy conserving, the other one not. Again, you can argue what you prefer in your actual calculation. Both of them are better when it comes to expectation values. And I've showed you a program how to use them as a swarm, either in the thawed way or in the frozen way. At the moment, the analysis we have is not good enough to really distinguish here in the error term whether the frozen or the thawed approximation is better. So the chemical physicists tend to believe that the frozen approximation is better. The mathematicians have a tendency to use the Gaussian beams, but I think by the end of the year I hope there will be, I'm close to having a hand on the O of epsilon and to pull out the error terms to say something at least about the leading order behavior. What I haven't addressed so far is a severe backtrack of all the stuff here. So the error estimates and all that game, at the end of the day, you arrive with some bounded functions, time and polynomial term that build up the remainders. Those polynomial terms fall on a Gaussian, you do a posteriori error analysis, and at the end of the day, everything is about knowing about the size of the moments of a Gaussian function. That's it, as simple as. And I have done the bookkeeping so far always in terms of the epsilon, but that's not honest. Those guys have a width, and it's not just the epsilon, it's what was encoded in the Q or in the P matrix. And this is the weak spot of the whole business. If those Gaussians get brought, there's those Qs here sitting around that eventually eat up all the benefits you have had in the epsilon. So in real life computations, epsilon is a fixed number and the Q is something that comes. And it might be that at the end of the day you're sitting on top of something really meaningless because the width has eaten up the epsilon. The good thing is, even though it is not yet done in simulations, I think I have convinced you that the error estimates we have are precise. And this is a computable quantity. It's already there. So what I think one has to accompany the simulations with corresponding error estimates in terms of Q and epsilon to really say what you are actually doing and then to say stop when things are really getting too large. Okay, and then of course there's an additional, so I want to support my claim that the width really can become bad. So we are talking about solving the linearized flow equation. So when we have a positively Lyapunov exponent, we know that this stuff might grow like hell. If you think about an inverted parabola, things just slide down with an incredible speed. The stuff gets incredibly broad, and then everything is bad. Yeah? So what my conclusion from all that analysis is, so nice they are individually, so nice they are when you put them together as a swarm, eventually you have to do more. So you have to see all these things as building blocks in, let's say, a tensorial approximation or whatever. So my favorite method at the moment that is around is something called Gaussian multi-configuration time-dependent Hartree. So this is a tensor ansatz with time-dependent coefficients, and the building blocks are those guys. And what you need to have is an inherent restriction on the size of them. You must not allow them to get too large, because then you see that here all the error estimates will become meaningless. So let's hope, so kind of the agenda that comes from all that analysis, that the Gaussian by themselves, the Gaussian as swarms, are fine, but you somehow have to put them in a cage and you have to restrict them. And then I think it's quite nice, because I mean all of us know how nice Gaussians are. If you want to compute the averages here, at the end of the day it's about averages in high dimensional space, but weighted with a normal distribution. Again, you can do them in the Monte Carlo fashion. Again, it doesn't mean that you need the potential energy surface in its full glory, but you just need it on a small carpet or on a certain size of the configuration space. You can do what is called direct on-the-fly computations. You don't need to build up the full surface, but you just evaluate locally integrals around that. So I think in principle it's very nice and very good, but you cannot use it somehow unrefined. And the analysis shows very clearly where the weaknesses are. And I want to advertise, finally, there is an upcoming Acta Numerica by Christian Lubich and myself, but basically you get an extended version of what I just presented here, more or less proof complete. So, and there's kind of, this is a very nice account of single Gaussians. This is work I did with a PhD student on this frozen Gaussian, and I think this will be the up-to-date review beginning of next year or whenever it will be ready. Thank you very much.